All right, so let's get started. So welcome everyone to another OCP Top session. This is call number 108. We have Stan from ENSCO. So just quick intro about Stan. Stan received a degree in geological science and mathematics from St. Cloud State University in Indiana University. Also a master in geophysics, and the Ohio State University. He received his PhD also in geophysics. He's a board certified geophysicist and works as an algorithm engineer and physical scientist at the UNESCO, with a recent focus on machine learning and using sensor data. So PNT experience includes optimal state estimation, inertial pedestrian navigation, assured PNT using GNSS and VLF, and integrity monitoring using machine learning. So today's talk is about hybrid machine learning fusion architecture for PNT situational awareness. So with no further ado, Stanley, the floor is yours.
Thank you for the introduction. So this effort was funded under ENSCO IRAD. We are looking at algorithms for pattern of life. And for this particular talk, we're talking about GPS integrity monitoring as one form of pattern of life. And so the objectives here is to use a hybrid machine learning architecture that fuses data from inexpensive GNSS receivers and directional antennas. So this is a dual approach. There's an unsupervised approach for general integrity monitoring, and then a supervised approach that provides classification information. For the unsupervised machine learning, we use dimensionality reduction that allows us to do clustering and visualize the data and also simplify analysis. And then supervised ML is used for classification of jamming and spoofing. And unsupervised provides just a general, do we have interference or not? Supervised provides more detailed information. And we use convolutional neural networks to look at spectrogram images of the GPS data. And then we also use directional antennas that allow us to determine which directions have the least interference, which directions have the most interference, and then you can apply that to array processing. And then on the end, also talk about feature selection and models. So we're combining both the spectrograms and also messages like metadata from the GPS receivers, and we fuse this all together. One application that this could be applied to is data centers. So in addition to positioning, timing integrity is also important when using GNSS. Again, this is a pattern of life approach using low-cost COTS GNSS receivers. And we acquire data using directional log periodic antennas, but we also have SERPA antennas as a reference, and those antennas provide they can acquire data from different directions and remove interference. And again, this is a multimodal hybrid approach. And here's one of the pictures of kind of the high-level architecture, where we have 8-element log periodic array. Each element is fed into U-blocks receiver. Each one of those goes through the machine learning framework, and then we also have the SERPA on the side as a reference. And here's just another slide showing kind of the framework of how the data is acquired. Again, each element of the array is fed into a uBlocks receiver, and then that's fed into the jamming spoofing detector classifier. And here's a high-level diagram of the machine learning architecture. So at the highest level, we have unsupervised learning that tells us yes or no if we have GPS interference. If we don't have GPS interference, we can stop. If you have GPS interference, and that can be fed into a supervised algorithm that provides more information on, classifies the data, jamming, spoofing, what type it is. And we have two different approaches. There are several different approaches for the supervised learning. We have learn kernels, so that's a spectrogram approach, computer vision approach that's used for classification. That's in orange. And then in gray is the feature selection in engineering. So those are, for example, messages in the metadata that are recorded with the GPS receivers. And also we've done some work generating some of our own features. And so these meta features and the spectrogram images are all combined in this blender concatenation layer, and then that provides a classification. So that's the big picture of the approach for the machine learning itself. And here's some examples of unsupervised learning. And so if you look at the figure on the left, it looks spherical. It's like a disk. In that, so that's no interference. And then towards the right, we have various types of interference. So to do this, I'm using principal component analysis to reduce the high dimensional data, that's the spectrogram, into image that can be displayed in 2D and visualized. And so no interference, you have the spherical object. So if you had no change at all in the data, it would just be a point in the center. And if you have random noise, you get this disk. That's what you have on the far left. And then the four images on the right are different examples of GPS interference going on that was known, during a test. And so you can see there's different types of interference, and it provides information on, what kind of interference that you're having. So that's unsupervised. And then this is an example of using log periodic antenna. So we have the spectrograms recorded here, and then we also have the PCA results that we saw previously of the dimensionality reduction. And then on the bottom, we have the plots of RMS position. So on the very left, you have the processing flow of the data. And then in the middle figure, you have antenna element 6, where you have very little interference. And then on the right is an example of one of the elements that has large amounts of interference. In this case, cyclical interference. And so what the main objective here of this slide is to show that different elements are affected by various degrees when you have interference. So some elements are affected more than others. And you can use that to your advantage to still record the signal and remove the interference. So you can use machine learning to tell you how to combine your elements to optimize your GPS data. And this was just another example of the data log periodic along with SERPA array. In this case, SERPA was not captured. And if you look at the ENSCO antenna, the log periodic antenna, some elements are affected while others are not. So that's the unsupervised portion. And then for supervised, we were using the images. So you can use spectrogram images to classify the data, what kind of interference you have. And then also you can use metadata. So what I've really done here is just showed an example of the approach that we might use to determine which features are useful in the GPS metadata, because some features are useful for interference detection, some aren't. And so here's just some example that approach that you use to determine which features are important, which ones are not. So here's some of the messages we recorded with the commercial U-Blocks antenna. We have C over N naught. That's a measure of signal to noise. There was 4 different parameters for that. And then the U-Blocks also provides what they call a jamming indicator 1 and 2, jamming state 1 and 2. And so I decided to use these 8 features as an example of how you would conduct this approach. So it's not necessarily optimal, but it is more used as an example of how you could determine which features are important. So the first thing I did is I just plotted all the features together visually. And so here I'm looking at the difference between jamming and spoofing. And so we can see some difference here just at a high level when you have jamming versus spoofing. So just looking at, can you use it to determine what kind of interference you may be having? And then I created a correlation matrix, and you can see the C over N naught features all are correlated. And then in addition to the correlation matrix, I also plotted a PCA loadings plot. So before I showed a score plot, these are loadings plot. And so you can see there's three main clusters, the C over N naught, jamming indicator, and jamming states. So if you're interested in a highly parsimonious model, you would use maybe one feature of each of those clusters. And then I also took another approach to look at which features are significant. So on the left, I specifically chose a non-parsimonious model. So parsimonious models only use features that are significant. They don't use redundant features. And so as an example, have a non-parsimonious model. I use K nearest neighbors. And then on the right, I used a more parsimonious model, a decision tree. And so for the non-parsimonious model, you can see all the C over N naughts are roughly equal in importance, with jamming indicators and the jamming states is distributed between them all. And then if you use a parsimonious model, you see you really only need to use 3 of the features. You don't need to use the other features. And then as part of analysis, performed a ROC curve on those features using a random forest, and also did a grid search on the parameter space, and then the 10-fold cross validation. So this is a very small data set. It's really not meant to show how well this is performing over general data, but it's more of an educational approach that we're looking at to determine which meta features from the GPS receiver are useful for classification. And then, so as a summary, we use unsupervised learning as the first level of the algorithm. It can be used on unseen data that has never been seen before, just to let the operator know, is there interference going on or not? And then if you have training data, then you can use the learn features, looking at the spectrogram images, using a computer vision approach. And then you also have handcrafted features that were engineered. You can be either directly from the GPS receiver itself, the meta features, or we've also created our own features that engineered. And so that's useful for cases where you don't have a large training set, fusing those two together. So we fuse together these unsupervised data and also the learned features and handcrafted features. So for the takeaway, using a robust, diverse approach makes it more difficult for the adversary to negatively impact all the antenna elements and receivers simultaneously. So that by using this log periodic array, it gives a spatial diversity. If you have a jammer or spoofer, you're going to be more affected by certain directions. And by having diversity, spatial diversity antenna elements, you can remove jamming and spoofing interference effects. Using a combination of learned and engineered features, and then machine learning is used to optimally combine and select features and antenna elements. And all this is using low-cost COTS hardware and agile machine learning software for a rapid deployment. For some of the future work, looking at using the algorithms to evaluate different forms of jamming and spoofing, and also look at periodicity within the spectrogram images themselves. We've had a very limited amount of training data, so one of the things we need to do in the future is label data and develop a database if the objective is actually to classify the kind of interference, and then train a model on the labeled data, and then work on developing near real-time implementation. So that's the presentation. If anyone has any questions.
Wonderful. Thank you very much. Like, I mean, it brings a completely new perspective to like the things we've been doing. So like in terms of, let's say, diversity, we've been like looking into different bands, different constellations, and somehow like, let's say, doing some survey between the two cross comparison to get the best. Again, I'm trying to avoid using the word fusion because I don't want to mislead like what we've been doing. So yeah, let's open the floor for questions. Judith, do you want to ask a question?
I was just putting the link to where
Sorry,
the
yeah.
recordings go. This is really cool stuff. It just went fast, and my brain's still catching up with a lot of it.
There's a lot of moving pieces.
Yeah. I guess in these models, it didn't look like you have like a local reference that's being used in your analyses to, advance your machine learning models. Is that correct?
What do you mean by local reference? You mean like a SERP antenna, or what's your reference?
Yeah, like 'cause if you're pulling, time off the GNSS satellites that you're utilizing here, if you have a local reference to compare against,
Okay.
for instance, in your spoof jam analysis section, something like that might provide additional functionality or capabilities or faster identification.
Sure. Yes. At this point, looked at mostly positioning, not so much on the timing end.
Okay.
But yeah, but definitely, you'd want to have a reference, for your if you're doing timing a clock, reference clock,
Hmm.
and that's where you could use, let's say, a clock that's not tied to GPS, or you could use your SERPA.
Stanley, maybe I can ask this question. Like, how do you see this if you want to expand this actually to multi-constellation and multi-band?
Yeah, I mean, you could do a similar approach and just use different bandwidths. So you'd have more spectrogram images, or you'd have across the different bands, and you could apply the same approach. You just build out by having more constellations and different, and then you can look at which constellations are being interfered with, which ones aren't. So that would be another form of diversity. In addition to direction, you'd have constellation diversity.
And let's say if you want to, again, back to what Judith brought up, like, let's say if you have, let's say, multiple local clocks, can you take advantage of that as well in this, or this is mainly just for GPS?
Yeah, this applies to a general pattern of life approach. So yeah, it could apply to various forms of data. We were looking at pattern of life using different kind of sensors. This is just one example using positioning, but it could be applied to timing. It could be applied to other types of data. There's nothing specific, for GPS positioning here. These algorithms can be applied to other kinds of data. So this is really just an example of the algorithms that can be applied to different data forms. So it can be applied to timing, positioning, non-GPS data, and it's all expandable, that you can take in, the architecture can take in various data streams and combine them.
Just
so it's
one
expandable architecture.
Yeah, go ahead.
How quickly can you detect the spoofing? In other words, how quickly, were you detecting it within microseconds, milliseconds, or it's more after the fact?
I haven't actually timed it, probably within a second or something like that. I haven't done the detailed analysis. It depends on what how fast you're sampling. So like if you're looking at let's say here's an example of, say, unsupervised learning here. So let's say you're recording data and you've determined what your background is as soon as you get a recording that is outside of that's different, you'll get a point that's outside of that cluster, and so you'll see that point as soon as you acquire it. But you need to determine kind of what your background is first. So if you've been recording for some time, and then, or what your background should look like, and then you get interference, it'll appear right away as soon as you record data.
Okay, but do you have to like record, in other words, an outlier here and there probably isn't an issue. I mean, you look at that picture and you have lots of outliers on the outside of the yellow green circle, right? And so what's to say that say that blue dot at the top was spoofing or not, right? Yeah,
usually what you get is you start seeing a pattern. So if you look at the other figures, you'll see that they have a pattern that's different.
Right. Okay.
So it wouldn't take you very long. It may take you a few seconds to notice that, but you'll see it. It doesn't take a long time to start seeing. Because it's not like a random type of noise. You can kind of see how this is a random type of noise when there's no interference. And when you get interference, you typically have some type of pattern to it that you start to pick up on.
And what does the hardware look like that you're running this AI ML on?
Right now, I've only run it on basically the PC at this point.
Okay. So PC. Okay, good.
Yeah.
All right. Thank you.
Haven't specialized the hardware yet. That's something that we would have to do in the future. It's been a research and development project at this point. It hasn't been production.
Got it. All right, thank you.
Sure.
Hey Stan, this is Terry. Quick question. With a local grandmaster and things like that, I think I'm using the word relatively with double quotes, but it's relatively easy to detect spoofing and jamming. You can see when, what you're getting off the satellites is drifting quite far from where you think you should be in terms of time. Was more interested in the case of if you think that this research would be applicable to mobile situations as well. Is there any reason why this wouldn't extend to, ground units or high flyers or fast flyers or anything like that?
Yeah, it could be applied to mobile just as well as stationary. Most of this was stationary simply so I can just verify that, if we did have spoofing and positioning, but it can be applied to mobile just as well. Just harder to do a ground truth on it.
Absolutely. Yeah, that's why it's the hard case. But yeah, no, this is
But
great work. And I was just wondering, again, as a not RF person, was wondering if things like Doppler effect or anything like that would change any of these graphs when you're moving.
not very much, because I'm just looking at the spectrogram, and it would be, pretty minor in terms of the shift.
Fantastic. Thanks very much.
So I have a follow-up question to that. How big is your AI model? Like, in other words, could I run this on a mobile phone? Or could my carrier run it on my phone to make sure that time's not being spoofed?
Yes, you can. So the unsupervised is really efficient. It's just PCA, and it's optimized. You can have like a LAPACK model or something like that. So it's very fast, mathematically efficient. And then the other one is just basically machine learning for using TensorFlow to classify the spectrogram. So all that could be applied on the phone. It's not very intensive. Nothing about it is highly intensive.
Cool. Thank you.
Any questions? Kishan, do you want to ask the question?
Yeah, thank you. Very interesting stuff. I still have to catch all the acronyms used, but you mentioned pattern of life. Is that a general technique, or is it something specific that you have developed? Or
Yeah.
my
So
question was, can it be used for in other areas just to identify abnormalities in trends or based on
no,
historic patterns?
no, definitely. That's a good question. So originally, this IRAD started off as a pattern of life IRAD, because in general, there's a lot of applications where you want to know if something's changing in your environment. And that's how this was developed. All these algorithms can be applied for general pattern of life. And then we happen to have some GPS data, and we had some interest in GPS spoofing. So that's what I showed here is really just a subset of pattern of life. It can be applied to many different types of totally non-related data. So this is a very generic approach that I applied here. It could be other sensors, and it's highly applicable to other types of data. Today was just a specific example of one type of data, how you could apply this type of algorithm. But that's why we developed this pattern of life IRAD for many different data types. And this is just one example.
Is there any available models or packages in open source for pattern of life? Or what would it be called?
I'm sure if people developed it, different kind of algorithms. There's a lot of different ones, like for anomaly detection. It kind of depends on what you're doing with your pattern of life. Change detection, anomaly detection. There's a lot of different algorithms out there for different applications. What we were looking at was kind of approach that could be used for a lot of different data that would provide both unsupervised. So the unsupervised would be normally known as anomaly detection. And so what I'm doing here is similar to what people do for anomaly detection. And then using the spectrogram part is really computer vision, supervised machine learning approach. And then the metadata is another type of supervised machine learning. It's usually doesn't use neural networks. You can use them. And so what I really did here was combine multiple pieces together into a fusion algorithm. So yes, a lot of these different pieces are used, but what we really did here is fuse everything together.
Okay. Thank you.
Yeah, thank you. Any more questions from the audience? So I'm just wondering, Stanley, how can we unlock the backup slides? What questions do we need for that?
Oh, I don't know. There's nothing really special here. This is it was more of a tutorial on how convolutional neural networks work.
Maybe we can go a little bit through that because it might be like useful for some of the folks here less familiar with CNN and all the
Yeah, because I didn't.
stuff.
I really don't know what the audience was. The backgrounds. So for the architecture, I'll go back to that high level slide. So you can see on the top is a green, that's the unsupervised part. And then we have a supervised part that's in orange and gray. And so on the orange part, we let the convolutional neural network learn the features, whereas on the gray, they're handcrafted. So a human actually engineers the features. So that's the key point to remember. Orange, the convolutional neural network learns the features, and on the gray, a human actually generates the features. So for the backup, so what I did here is, so one way you can do that is using a Gabor filter bank. And so what you do is use what they call convolutional kernels. And what you multiply that convolutional kernel with your data, and you get some output. And then what you do is feed that output into your neural network. So if you have a convolutional neural network, you have the convolutional part that does this work for you. So in this case, in a Gabor filter bank, the person actually designs the filter. And when you use a convolutional neural network, the neural network actually learns what that filter is. But this is kind of a step halfway there, where the human actually designs the Gabor filter bank. And then the output of that Gabor filter is what's actually fed into your neural network. Usually would use a dense neural network. So instead of using the raw images, what you're actually feeding the neural network is the filter data, the results of the filters. And then this is just one example from the literature of convolutional neural network. So this is an old simple architecture, VGG16. And so what you do is you bring in your input on the left, your image, and then it goes through these convolutional filters, and the neural network learns what the right filters are, what kind of optimal filters are. And then on the right are activation. So it shows what pattern will maximally excite the neural network. And so this would be the output of the convolutional filters. It's a filter bank. You bring your data, you bring your image in, it goes through this filter bank where these filters are convolved with your data, and then you have this output. And it's this output that's actually goes into the blue part on the bottom here. That's the learning part. And it's results of all these filter banks that go into the dense layer that does the classification. So that would be that's the orange part. Image goes in, goes through this large filter bank. It's the output of this filter bank that goes to the dense learning layer, not the actual raw images, not the actual spectrograms, but the data that's been convolved through this filter bank. So that's the left part, the orange, and then the gray gray are features that are directly fed in, the engineered features. It could be like C over naught, various jamming indicators, physical model outputs. So on the right, you have these handcrafted features. On the left, you have these images that go through the filter bank. And then all this is combined in this concatenation layer that gets fed into this dense learning layer that does the actual classification. And then usually use a softmax layer on the very end that gives you an output between 0 and 1. So a percentage of, it could be either interference or what type of jamming and spoofing it is. So that's all I had in the backup slides, was just a kind of a brief tutorial of how neural networks learn features as opposed to directly programmed features.
Interesting. Really interesting.
So more of just educational slides.
Yeah. I'm just wondering, how can we, let's say, I mean, do we have access to this? Is this like open source, or is just like right now, or is going to be, I mean, I know a lot of it is under development. Is it going to be open source? Is it just going to be a product? Any of that?
Most likely a product. I'll probably leave that open to program manager, how they want to do that. But I most likely see it as a product.
Okay. But the concept is, I mean, open.
Yeah, the concept is open. I'm using open source tools for this.
Yes.
I'm using scikit-learn for the gray part, and then using Python and using TensorFlow for the orange part.
Yes.
I'm using all open source tools. All the software is open source. Yeah. In that sense of how I'm building this, is there's no like pieces that I just develop from scratch. In terms of software, I'm using libraries and things that are available.
Yeah,
it's no specific
data
kind of
or something that will make it, like, let's say, proprietary. Maybe again a light version of this can be open sourced or something like.
It could be, and depending on what the application is too. It depends.
Yeah.
Some data can't be open source. Some can.
Yes. Yes.
Depending on your application and what kind of data you're using.
Yeah. All right. Any more questions from the audience?
I have two questions, Ahmed.
Go ahead. Go ahead. Go ahead.
Can I go ahead?
Yes. Yes. Go ahead.
So the first question is, do you have data from some empirical analysis using your technology to show how effective it is in detecting all these security threats?
Yeah, so that's kind of went through that example on the end there, where I actually had some data that was interfered with, and we could tell the two different types. We could differentiate the two types of interference. So at a high level, we could see when we have interference and non-interference. So this was actual data that we acquired where we had interference during a test, and we had ground truth. And so the answer is yes, I could see when we have interference and when we don't have interference, and it matched up with the ground truth. And then also we've looked at, in this case where we're looking at some of the supervised, we could see different types of interference. We could classify it, and then also when using supervised and unsupervised, you can see there's different kinds of interference, and we could see different patterns when they had different types of interference. So yes, we've shown that we can detect interference during live tests.
And my second question, I work on cyber physical systems, and in these systems sometimes they suffer from synchronization attacks, where, for example, they change, there is somebody, an attacker or an intruder, change the timestamps of the measurements instead of changing the measurements themselves. So can we use your machine learning technique to discover such a kind of time synchronization attacks in cyber physical systems? For example, I was reading about something called first difference aware machine learning, FDML, which is a classifier to detect such a kind of cyber physical systems attacks. But I have to admit I'm not expert in that approach. But I'm wondering if your approach can provide better results.
Yeah, so I believe what you're asking, and you're noticing anomalous behavior when you're having a cyber attack. So that's where you use this kind of unsupervised approach and say, okay, there's an anomaly occurring. This is not normal. And then if you want to know what, if you have, let's say, training data, then you could do a supervised approach saying, well, maybe this is this type of attack.
So
but that's
so you can train your neural network to detect when somebody changed the timestamp of the measurements itself in a cyber physical system, right?
You could train your neural network to look for specific, but you have to have training data to do that. If you use the unsupervised approach, you can just look at it and say, okay, is there an anomaly occurring or not? It just
really,
sets up
you can apply your neural network into any of these systems or applications.
Yeah, you could.
How you train it, right?
Yes.
Got it. So whatever you provide, I can use it to train the neural networks to detect not just anomalies like this, or detect that somebody changes the timestamps.
Yeah, if you have something specific that you're looking for, then you use a supervised learning. You could use a neural network to say, okay, yeah, this is going on.
You're right. So supervised learning is more suitable. I agree. Thank you very much.
Sure.
All right. Any questions from the audience?
Yeah, this is Brian Sexton at ENSCO. That was helpful to understand a little about some of the attack vectors that some of the critical infrastructure are subjected to. But if others have other anecdotes or details about the types of threats that you're interested in detecting, that would be really interesting to us to hear.
All right. So, thank you again for the presenters. And we'll give back everyone, what, 15 minutes? And we see everyone hopefully in 2 weeks. Or we might have, again, stay tuned, like check on the wiki. We might have a talk. Again, we're still looking for, like there is a speaker that might get on the Friday, like not this coming Friday, the next one. And we have also definitely in 2 weeks the usual one on Wednesday, and I think let's see who is the presenter for that one. That will be from Jason. Yeah, Jason Ashraqnian is going to give us a presentation about time-based like computation in LLMs using spike neural networks. And no more questions, no further ado. We'll see you guys in 2 weeks.
Well, thank you for organizing, and thank you for all the questions. It provides insight in terms of your interests and kind of things that you're working on.
You're very welcome. All right. Bye, everyone.
Bye.